Hello there. In today's lesson, we're going to look at section 5.3, which is cylindrical shells. It's pretty much the same as what we just did in 5.2, but it's a new technique for finding volumes. And let's get started. All right, so the idea is that we're going to break up a volume into concentric shells. And so it's called the method of cylindrical shells. Sometimes we just call it the shell method. You'll get used to that pretty fast. And sometimes it's easier to use compared to the disk method that we just saw. So the idea here, and you can see from the picture how this works, that there's an inner radius, we call it R1. Then there's an outer radius R2. And the height here is H. So the volume of a shell is the outer cylinder minus the inner cylinder. We saw earlier in chapter 5 that the volume of a cylinder is 2 pi r squared h. So what we're going to do then is just derive a formula for the volume of a shell, and that's on the next slide. So the idea here is that, if you have a big outer cylinder and you subtract the smaller inner cylinder, what you have left is the volume of the shell itself, right? So it's like big cylinder minus little cylinder. And the other thing I want to point out is what R and delta R here, and those are used on the next slide when I compute the formula. Delta R is the thickness of the shell, and R by itself is the average radius. So it's if you average R1 and R2, it's the average radius. And we need that when we compute the formula. So let's compute the formula for the volume of the shell. So we know that so V1 is the outer cylinder, V2 is the inner cylinder, so we're going to subtract those. So I just plug in the formula for the volumes of each cylinder, right? So the outer the outer cylinder is pi r squared h, but R2 is the outer radius, R1 is the inner radius. Then I'm going to factor out all the common factors, right? So pi and h are common factors. Then I'm going to use difference of squares formula to split this, to factor this, right? This is a difference of squares, so I can factor it. R2 minus R1, we've already called delta R on the previous slide. That's the difference, or it's the thickness of the shell. And R2 plus R1 is close to the average radius. But in order to make this an average radius, we just have to divide by 2. So what we're going to do is we divide this by 2 and multiply this by 2. So we're basically multiplying by 2 over 2. We're just splitting the 2 in the numerator and the 2 in the denominator to get this. So I move the h here. This stays the same. I put a 2 in the denominator, and this 2 would technically be in the numerator when you multiply, right? So what we're doing is rearranging. This is delta R. This is what we called R on the previous slide. This is just the average radius. And so we get this formula. So this is actually the formula for the volume of a thin cylindrical shell. Right? And you can measure the thickness of the shell. We know the height. You could compute the average radius, and we know 2 pi. So this is very computable. But we want to do some calculus, right? So the idea here is we need a more general method. So let's see how that works. This is a mnemonic for how to remember it. 2 pi r is the circumference. H is the height. Delta r is the thickness. So whenever we see these formulas later in this section, we're going to see a lot of stuff that looks like this. Just remember that 2 pi goes with the r. H is by itself, and whatever else is after that goes by itself. So 2 pi r is the circumference. So here's the idea. Imagine we have some function, and we want to rotate it around the y-axis. So we want to take this, whatever it is, between a and b, and spin it around the y-axis. When we tried to use disks to do that, you'd have to have x as a function of y in order to go around the y-axis. But it doesn't look like we'd be able to do that with this function. So the idea is if we build shells out of it, we can take a whole bunch of shells and add them up. Okay, so we take that region AB, divide it into n subintervals, so we're just going through the theoretical underpinnings of why this integral works. We're assuming equal width, right? That was given in the previous setup. And we're going to introduce a new notation here. It's xi. This horizontal line is called bar, so it's xi bar. It's the midpoint of the subinterval. It doesn't have to be the midpoint. When we do integrals, you're allowed to pick any point in the interval. So we're using the midpoint so that we can go back and use this formula. Because remember, this is, right here, this is the average radius. So if we pick the midpoint of the two radiuses, it'll be right in the middle, and we can use this formula. So that's why we're doing it. You're allowed to pick any point you want. We're picking the midpoint. And so you have a rectangle here. This is like a little typical rectangle, and that's what gets spun around and makes a shell. The base is xi minus 1, xi. I is just any number. And then xi bar is right in the middle. And then we compute f of xi bar to get the height. Right here. We rotate that around the y-axis, and then it gives us our cylindrical shell. So we're using the average radius, so we can plug it in here, because we already derived this formula on the previous couple slides. Right? So we have 2 pi... so 2 pi r is the circumference. So the idea is if you take a single point and spin it around, or like a vertical line with no thickness and spin it around, you just get a circumference. Like the distance it travels around the circle is the circumference. But we need to include the thickness of the shell as part of the volume, and we need to include the height of the shell as part of the volume. So the idea is like this is like each of these is one-dimensional times 3. This is a 3-dimensional object, right? So what we're going to do is just stack up a bunch of these shells and then use calculus, because why wouldn't we? So let's say you had like, how many shells are here? Like 5, 1, 2, 3, 4, 5. Yeah, let's say there's 5 shells. Those 5 shells are a pretty good approximation. But if you have more shells, the approximation will get better and better. So the limit of the volumes of the shells summed up is just an integral. And that's what this slide says. So the volume is approximately equal to the sum of the individual shells, which is just this. And if we let n go to infinity, more and more shells means better and better approximation. And it turns out this is just a Riemann sum. And as you did in Calc 1 a whole bunch, and so far in this class a couple of times, it just gives us this nice integral. And you can see that this is exactly matches the formula from a few slides ago, which was circumference, height, thickness. So the dx is the thickness. That's what we're integrating over. So when you're trying to figure out if these integrals are dx or dy, look where the rectangle is thin. The direction it's thin in, the very small thickness, will be the direction of integration. So here, these rectangles are thin in the x direction. So these were dx integrals, but they could be dy integrals. And so here's just sort of the official use of the formula, right? So the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals f of x, from x equals a to x equals b is this volume. All right, so let's see how this works. Let's go ahead and do an example. And I'm just going to use the formula directly. All right, so we're going to go around the y-axis. And our function is y equals 3x times x minus 1 squared. And the line y equals 0. So this region, it's just bounded at the bottom by the x-axis. Y equals 0 is the x-axis. And of course, we just find the intersection points first. Sometimes the graphs are good enough to find the intersection points. Sometimes they're not. In this case, this is really easy algebra to do, right? You just set this equal to this, and you can see clearly that x equals 0 is going to be a solution, and x equals 1 is going to be a solution. And there's only 2 intersection points. And when you see the graph, you're like, oh yeah, there's 2 intersection points, right? 0, 0. and 1, 0, right? So you always want to graph the function. You always want to shade the area. And then you want to draw a typical rectangle. And that rectangle, so I just drew it in the middle, and then imagine spinning it around the y-axis. It creates a shell. We have a formula for the volume of the shell. So all you have to do is set up the integral, and we can see what's going to happen. The circumference here is the distance from whatever, so we're in, this is a dx integral, so we're measuring x distance to the center of the rotation. Well, the center of the rotation is the line x equals 0. So it's just the x value of wherever this shell happens to be. Remember, there's going to be lots and lots of these things, and we take the limit. So, you know, what is the x coordinate of this? Well, we're on the x-axis, so it's just x. So the circumference, if the radius here, if the radius of this circle is x, you go around the circle is 2 pi. So the circumference calculation will be 2 pi x. The height of the shell, we can see clearly, is the function, 3x times x minus 1 squared. And the thickness, we are doing a dx integral, so the thickness is just dx. So there's the generic formula. I'm always going to just start with the generic version of the formula and then plug in the specifics, right? So we're going from 0 to 1 in the x direction. The circumference we already figured out was 2 pi x. The function itself is given in the problem, and the dx is the thickness. It just stays dx. This is a really easy integral to do. Right, so you just FOIL everything out and pull all the constants to the front. Do the integral. And of course, you guys know how to do this stuff from here. So once you get it to here, it becomes a relatively straightforward problem. And as I've stated before, it's more important that you can set these integrals up compared to solving them. So the most important step to get to is right before you do the integral. So this would be just set up, this stage here, but let me go back. This would be considered set up the integral, do nothing else. This would be set up the integral and simplify, evaluate the integral, and then get the answer. So there's lots of steps. Most important step is setting up and simplifying right here. So if you're worried that you can or can't do stuff like this, just pause the video or go back and do this problem again. This is a pretty typical problem. In fact, this is one of the problems from your homework, as you probably guessed from the picture. All right, let's keep moving. So now we're going to use shells again. We want to find the volume of the solid obtained by rotating the region bounded by the given curves around the line y equals 5. This is a little bit different of a problem. It's still going to be an x integral, right? Because we're going around the line y equals 5. But because we're using shells, it's going to be thin in the y direction. So we're going to have to flip it and do a y integral. Now you could do a problem like this with disks in the x direction, but it's no fun to solve this for y because you'd end up with a plus or minus square root. You don't want to do that. All right, so let's see how this works. So the first thing I do is I graphed it. So I graphed this in Desmos. Our lines were given as y minus 6 squared, so that's the parabola. X equals 1 is a vertical line here. And then we're rotating around the line y equals 5. Right, so go back and look at it again. Right, we're rotating around this line, this function, so the region bounded by this function and this function. So it's this shaded region here. Again, we're using shells, so you want to figure out what are the two functions we're trying to find in between. If you tried to draw a vertical rectangle here, you'd end up trying to subtract the function from itself, or you could use disks, but again, disks wouldn't work here because your outer and inner function are the same function, and that creates big problems. So by using shells, we know that this region is bounded by x equals 1 and x equals y minus 6 squared. So it's a much easier setup. And as you go through problems like this, you'll kind of learn when to use shells and when to you'll learn when to use disks. So that's my region. But remember, we're rotating around this line y equals 5. Oh, need to do the intersection points too. So the graph was pretty good. It's easy to see that it's 1, 5, and 1, 7. This would not be hard to solve if you had to solve it. You would just set it equal, FOIL it, factor it, and you'd get the same answer. So not hard to solve this, but the graph is pretty good, so we can use the graph. So when we go to rotate this thing, remember, here's our typical rectangle. Here's the line we're rotating around. So I kind of pulled back the zoom a little bit, and you can see what this looks like when it turns into a circle. So this is our shell. So we know what the height of the function. So we're kind of like everything's kind of on its side. So the height is actually the width, but we're calling it height because we're talking about this cylinder. The cylinder just happens to be on its side, but still think of the height as the thing that's perpendicular to the circular parts, right? And the center here is the line y equals 5. So we're basically taking this shape and kind of making like a jello mold, sort of what it would look like if you imagine this whole thing rotated around. Your homework does a good job of having you visualize these regions, though. So just try to sketch it out or use Desmos. On a test, you're going to have to draw it by hand in some form or another. So practice how to draw these things, or at least sketch them, so that you have some idea. Because you're later on, you're going to have to figure out when to use shells and when to use disks. Right now, we're learning about the shell method, so you're doing the shell method. But in the future, you may be given problems where you may have to decide which is better, shells or disks. And you have to be able to kind of visualize it and figure out, well, the arithmetic's easier here, but the algebra is easier here, but the calculus is easier here. So you'll end up with some choices with problems later on. All right, so back to the integral. So now we have to kind of figure out what's going on. So remember, we need circumference, height, thickness. We can see that the rectangle is thick in the y direction, so it's going to be a dy integral, so the thickness isn't too hard. The height of the function of the rectangle is the difference between these two functions. So one thing you got to remember, if you're in the x direction, it's always top function minus bottom function. If you're in the y direction, it's right minus left. It's always big number minus little number when you do these things. If you do it the other way, you will get a negative number, and it won't make any sense. So it's going to be 1, right, minus this. Then we do the circumference. The circumference is 2 pi times this radius. So this is a shell. What's the radius of this shell? Well, remember, this thing's moving, right? Just looking at it now, you might say, oh, this radius is 1 because it's 6 minus 5. It's not how we do it. This is this shell moves as a function of the integral. So the idea is no matter where you are in this region, you are measuring where you are by its y-coordinate, but the distance between whatever that y-coordinate is and the center is just going to be y, because it's above the line y equals 5. So it's y equals whatever it is, so y minus 5. So this radius is y minus 5. So for this rectangle here, you can see when it's at 6, it's 6 minus 5, which is 1. But if we start up here, it's going to be 7 minus 5, it's going to be 2. So this thing starts out at radius 2 as the shells come from the outside in. And you end up at 0, right? Because the intersection point, 5 minus 5 is 0. Right? So we just talked about all this. So instead of thinking in like big grand formula terms, break it into its individual sections. Circumference, height, thickness. And just think of the circumference as 2 pi r. Look at the sketch, look at your graph, and just try to figure out what is the radius of this circle that's the base of this cylinder, right? Well, it's top minus bottom. The top is given by the y-coordinate. The bottom is the line y equals 5, so it's y-coordinate minus 5, so we get y minus 5. And we already talked about the height of the shell. It's right minus left, so it's 1 minus quantity y minus 6 squared. This stuff takes a lot of practice. Don't panic if you don't get it the first time. Just keep working at it. But you have enough homework problems in this section to keep you busy. Just make sure you're doing exactly what I'm doing. Be very systematic with it. If you start cutting corners, you're going to just get these wrong because there's too much setup. You have to think about it too hard. So take your time, go through it slow. Plus, it'll be on a test, so you definitely want to practice these methods. So the rectangle is thin in the y direction, so we have a y integral. And here again, you can see I just wrote the generic version of the integral. Y doesn't mean y. This just is a stand-in for 2 pi r, right, for the circumference. So it's like 2 pi, so it's going to be y or y minus something or something minus y. And then that's the height as a function of y. And of course dy. So I just plug everything in. So we're going from 5 to 7. Let's go back and look at the picture to see why, right? Your integral goes from low to high. So we're going this way, right? The rectangles are getting bigger and then smaller. So these shells are starting off, it goes from smaller to bigger. So the shells start off really small. The shells get big and then the shells get small again as you scan from 5 to 7. Then the radius, so again, this y is just a stand-in. This isn't a formula. This is just like a placeholder. The radius of that circle, so the radius of that cylinder, is y minus 5, as we discussed on the previous slide. The height of the cylinder given by the right function minus the left function, and of course dy. So, pretty easy integral, right? You FOIL it out, pull the 2 pi to the front. If you need to pause here to verify that you can do this, go ahead and pause. I'm just showing you the highlight reel here. Once you get to this point, it's simplified and set up. So again, a problem on a test might say simplify, set up and simplify, do not solve. You would stop here. But you may have to work through it by hand. I may ask you to use your calculator to solve it. But you still got to get it set up to here, and then you can type that in using the method we saw earlier in Chapter 5 for finding integrals on your calculator. And you get 8 pi over 3, which is about 8.378. So, as discussed previously in Chapter 5, this is an exact value. This is an approximation. On a test, I might require an exact value. I might just tell you to use your calculator and round to 3 decimal places. Regardless, when you get to this step, you might as well check your answer. So you can type this into your calculator and get that. You can solve it by hand and get that and check if they're the same number. And if they are, then you did it right. It's very difficult to make a mistake in this section and still get the right answer. That just doesn't happen very much. So if you goof, you'll get the wrong answer pretty much because there's just too much going on here. Okay, so we saw a dx integral. We saw a dy integral with a radius that was something other than just x or y, right? It was a radius here was y minus 5. That's very common. So let's look at one more type of problem. So now we're going to rotate. We're doing another x integral here. Our functions are cosine to the 4th x, negative cosine to the 4th x. In this region, and we're going around the line x equals pi. Then we're going to use technology to evaluate this. You'll see why when we get the integral set up. We're going to have an integral that we don't know how to do. We're not going to learn till probably halfway through Chapter 7 how to do the integral that you're about to see. So let's find the intersection points. It helps us when we draw the graph and set up the integral. So you just substitute one equation into the other, add cosine to the 4th x to both sides, divide by 2, take the 4th root. You're allowed to take 4th roots when 0 is on one side. And cosine x equals 0 at x is pi over 2 plus pi k. And so the domain is given as negative pi over 2 to pi over 2, so the intersection points are negative pi over 2, 0, and pi over 2, 0. I know some of you are thinking pi over 2 plus 2 pi k. The period of cosine to the 4th is pi. So just wanted to point that out in case you forgot it from trig. Because cosine squared turns all the negative values positive, so the period goes from 2 pi to pi. So I just did a little shortcut there. Maybe you remember it, maybe you don't. If you need to prove this to yourself, you can go back and open up your trig book or just look up online. But this is the period of cosine to an even power. So draw the graph, right? So here's cosine to the 4th x is the top function. Negative cosine to the 4th x is the bottom function. Our typical rectangle is vertical because it's top minus bottom. And we're rotating around the line x equals pi. So we're taking this like teardrop kind of shape, whatever you call it, UFO shape. We're going to just rotate the whole thing around. And just like we did before, we need circumference, height, and thickness. The circumference here is the distance between this and this, right? But you always do right minus left. Here, the center of this thing is on the right. So as we rotate it, the center of those circles, the center of that cylinder is on the right. So it's pi minus, well, this thing moves around. It goes from negative pi over 2 to pi over 2, right? This thing, it goes from the left to the right, and it gets bigger and then smaller. So it's pi minus whatever the x value is here. So it's just going to be pi minus x. So in this problem, what we saw is, so the reason I wanted to do this problem is because it makes sense for the height of the function to be top minus bottom or right minus left. It's harder to see why for the radius that you need to do top minus bottom or right minus left. It depends on where the function is. It depends on where the shaded region is compared to the line you're rotating around. If this whole thing were on this side, it would be x minus pi. But this whole thing starts on the left side. So it's pi minus x. It's right minus whatever this coordinate is, which is x. The height of the function is pretty easy, right? It's top function minus bottom function. So it's cosine of the 4th x minus negative cosine of the 4th x, which is 2 cosine of the 4th x. And it's easy to see that that's what's going to happen, right? This thing here is the same size as that. So when you subtract, you just double the size. So we're ready to set up the integral, right? So this is in the x direction. We're given all of these numbers, right? We're given negative pi over 2 to pi over 2. Again, I just put x in here as a generic placeholder for the radius. We know the radius is, in fact, pi minus x. And we know the function is 2 cosine of the 4th x, and our thickness is dx. So that's set up, but it's not simplified. That is set up and simplified. I just pulled all the constants to the front. We have a 2 and a 2 pi, so it's 4 pi. We do not know how to do this integral. You won't learn for another few weeks. So we just have to do it on our calculators, right? Just use the integral f dx function that we talked about at the beginning of chapter 5, and you get a decimal answer. There's no way to know what the exact value is for this, because we just don't have the tools yet in this class to do it. So that's basically it. You've seen the 3 main kinds of problems. The radius can just be the x or y coordinate. So the radius of the cylinder. The radius could be top minus bottom, right minus left. It just depends on where the function is relative to the center of the circle. And the height of the function could be top minus bottom or right minus left as well. But when you're using this formula, just remember that this thing here is just a stand-in for the radius. So it's not x. In this case, it was pi minus x. But that's okay, because the picture told me what the radius was going to be. All right, well, that's it. If you have questions, post them on the discussion forum or message me. And next video will be the last one from Chapter 5. We're going to do Section 5.5 next. So that's it for today, and I'll see you guys next video. Bye-bye now.